Okay. Yeah, so my name is Alan Baker, and I'm going to present a framework for designing programmable modules. Okay. First, I just want to say that I really like Chisel. As a software developer who has dabbled in creating hardware only occasionally so far, I found it a lot more enjoyable to learn and use than Verilog. Though my knowledge of both languages is still pretty limited, the focus on hardware generation in Chisel rather than description really appeals to me as a software developer who wants to automate and parameterize everything I can see. The learning process was really improved with the extensive documentation, including the bootcamp and API docs. The abundance of open source projects provides a lot of really valuable examples of how to use certain features and utilities. The building blocks in the language itself make it easy to get started creating hardware from scratch and to test it at an early stage. Which I like because I'm a test-driven development fanatic. So I do that with my software. I would like to do that with my hardware. Finally, Scala, which Chisel is based on, is a really powerful language for writing clear and concise code. All that being said, there are still difficulties with hardware design that even Chisel doesn't fully address. The simple circuits that are taught in the tutorials and boot camps are fine for just getting off the ground, but there is still a big gap between those and what's required to make like a processor or like any like more complex block that has to fit into a system. The interfaces between like memories and caches and other blocks require synchronization or diplomacy, which involves keeping track of like maybe multiple sets of ready valid signals in addition to the internal state. And if you want to improve your performance of your block with techniques such as like pipelining or parallelization, that just increases the number of things that you have to keep track at once. And this is a problem because as the design gets more complex with more state elements, it's harder for like software developers who are used to writing mostly procedural programs, like such as myself. It's hard for them to really wrap their heads around like the concurrency of hardware when it's like written like code. So and so we want to try to solve this because like creating these complex blocks and like moving a step above the like tutorials and boot camps is necessary, and processors, which are more complex, are desirable targets for new designers. We want to not only design hardware, but we also want to run like software that like we write or someone else writes on them. So processors are an ideal like target for that sort of thing. And there are many of the materials required to create processors already out there, like open instruction set architectures and tool chains and software compiled with those two tool chains. So like once we actually like can create that design, then there's going to be a lot that we can do with it. Okay, so there's kind of a problem in the hardware design space where we have it's an owl drawing problem where we have like some circles that represent like the existing documentation and language facilities. But then there's basically just like the open source projects like Rocket and things like that are like the owl. So we kind of need, I think we need a little more guidance about how we go from like step 1 to step 2. So that's what I propose to do with the processing module framework, which is like the next step in hardware generation. And so what I'm aiming for is to build more elaborate generation patterns, going beyond just the existing built-in standard libraries that give you queues and shift registers. So things like I will say that things like diplomacy that was mentioned before And DSP tools are a step in the right direction, where you basically just add in parameters or mix in traits to like add in whole interfaces for bus protocols to tie like a whole bunch of blocks together. So I want to do something similar for processors, where you basically define an ISA specification in a similar format to what you see in the actual document. So like these snippets from the RISC-V ISA, most other ISA specifications have similar formats where you have the user visible state and you have the instructions, their encodings basically, and then their effects on that state or the I/O. So my goal is to create a framework that eases the transition from this spec to an actual implementation. So I think we can use Chisel to do that. Yeah, so basically, I want to create a framework that generates the hardware given an ISA. And it basically contains a sequence of instructions that define their dependencies on state or I/O, and then the operations once those resources are available. The state, again, is like declared alongside the instructions so that all the instructions can access that. And in addition, you can also declare combinational units like ALUs to improve the resource usage of your processor so that like things like adders or multipliers aren't duplicated for like between several instructions. And in the future, I do want to eventually add in options for this or parameters for this this parameterized processing module to enable or insert structural features like pipelining or speculation or reordering that like you may want or not want depending on your application. They will improve performance, but at the cost of additional hardware resources. And also, like my initial implementation mixes in well with other Chisel code as it inherits from module and like features like pretty standard decoupled and valid interfaces. Okay, so here we have the beginning of the definition for the processing module class. So right now it just contains a few parameters for like data widths, address widths, and instruction widths. And then that's followed by like this pretty simple I/O declaration that has like two bundles for instructions and data. The instruction like bundle like just has the input port for like the actual instructions coming into the processor, and program counter, which is right now it's fixed to 64 bits because all of my test programs are exascale, exabit size. But I'll like convert that into a parameter soon. And then that's followed by the data bundle, which like just has a decoupled port for incoming data and an output for address for data like stores and loads and like values for storing into memory. So following the I/O is this single abstract method called init instructions. And you might notice that this is an abstract class. So basically, you're going, your processor implementation is going to inherit from this. And when it does, it needs to define this init instructions class to actually return the instructions and common logic for those instructions. Okay, so yeah, so you'll notice that like this returns instructions, needs to return an instructions type, and so that's defined here. It's another abstract class that has like one more abstract method called logic, which is like returns actually like the list of actual instructions. And so basically, this is another abstract class where you like you have like one instruction logic class for each instruction that you want to have in your ISA. So basically, you parameterize that by the name and whether it depends on like data input or output, like from the memory. And then you also have to define like how it's encoding, which is what you do with this decode method here, and then like the execute method, which defines like the operation that it will do with that with the common state, or like the data coming in from memory. And then optionally, if you do like set these to true, the data in depend or data out depend, then you need to define these load or store methods to provide the addresses to fetch data from. And just one more thing, in addition, inside your instructions class here, in addition to defining this logic method, this is where you insert your common logic, like your register file or your ALUs. Okay, so I think it's best explained with a simple example. So this is just a very simple module that has only a few instructions for incrementing some internal registers. So you can see it extends from processing module. It has some functions here for extracting fields from the incoming instructions, and then it defines the init instructions method, which contains the register file, which is just a sequence of two registers. The widths are parameterized by dwidth. And then following that is the logic method, which returns a sequence of instructions here. And right now you can only see a no up instruction, but I'll go into more instructions that you can add in later that demonstrate different abilities. Okay, so this is one instruction called increment 1, which doesn't depend on any data, on any memory, loading or storing to memory. It's defines this decoding, which basically just checks a code field in the instruction to see if it matches a pattern. And then in the execute method, it just says that it will increment the specific register in the instruction by 1. When reading from memory, basically the same thing. It checks the code here, but it says that it depends on incoming data from memory with this parameter here. And the load, since it depends on incoming data, it needs to define this load method and provide the address that's included in the instruction. And once that data is available from memory, this execute method will be this logic from the execute method will be run to increment the data in the register file by the data from memory. And then write from memory, write to memory, it's a similar thing except that you have a data out dependency, and you overwrite the store method to return the address that you want to store to. And you can also, there's also the program counter exposed to your instructions, so that if you want to branch or jump, you can increment the program counter directly from instructions as well. Okay, so that's the basic idea. I don't really have any results with a real instruction set yet, but I plan to in the future. And so it's basically just been testing with this simple address adder module. So I've tested, it was easy to test since it has decoupled and valid interfaces. It was easy to test with the ordered decoupled hardware I/O tester, which is easier than the basic peak poke tester. And as I said, enables a test-driven development style for hardware. So I started using that, and that worked fine for a while. But then I actually wrote my own flavor of that sort of tester with a decoupled tester, which is contained in the same project. And it has several changes, including it orders the input and output events together. The order decoupled hardware I/O tester kind of ordered them separately. And it fails when the maximum tick count is exceeded. It automatically initializes all DUT inputs. and it has like a clear messaging, at least from my point of view. And yeah, so this is an example test, and you'll notice that looks a lot like order decoupled hardware I/O tester, where you basically just list a series of output and input events. So this is just one test that tests incrementing a register by 1 and then storing that in memory, and that's how you can check the values of your register set. Okay, so that's basically it. As I said, I plan to actually provide a proof of concept for this with real instruction sets like RISC-V, OpenRISC, and OpenPower. I want to improve the user phase to decrease boilerplate code and actually fix a bug that excludes the user state from waveforms. And as I said as well, I want to add more options to the constructor parameters to enable these structural features like pipelines and prediction and reordering. And so you can follow the progress of this project at this URL here. Thank you.
Thanks, Alan. Any questions? We have a minute. Okay. Going once, going twice. Okay. All right. Thank you. Thanks very much. Okay. Thanks again for